Okay, so I forgot what this one covers. I guess we'll see. Oh boy, phased arrays. uh, okay. I guess it's true. They claim that if you've got something like a big Yagi, especially for the lower bands, like 160 or 80 or 40, they're very large and you need to get them fairly high off the ground. So you really need to put them on top of a tower and you really need a rotator. Otherwise, you're only beaming in one direction all the time. One way to get around that is to use what they call a phased vertical array, where you have multiple vertical antennas set up and you can send the signal to each antenna uh, in a different phase. So you can either have them 90 degrees out of phase, 180 degrees out of phase, or in phase, and it affects the pattern. They do this kind of thing with radar systems, where uh, you can have a bunch of little tiny dipoles in an array and change the phase of the signal, and actually, without moving the antenna, you can move the beam around by changing the phase. And that's how a lot of the radar antennas work and sweep like that. We're only going to deal with uh, two verticals, keep it simple. So they're going to have two quarter wave verticals, and we're going to phase them differently and see what the effect is. This is an example of what like a military or commercial phased array would be. And you have all these little dipole antennas, and you're feeding the same signal, but you're changing the phase of it, so you can effectively change the beam angle.
You ever see pictures of a cruiser destroyer of the U.S. Navy? Those big octagonal panels, those are phased array radar.
Yeah. First one I saw was a Russian one called a flat-lid. And it was about 6 feet in diameter, had 1,024 dipoles on it. And it would rotate and tilt, but then they still phased it. It was quite interesting. Of course, that was 40 years ago. It's amazing what they might have today. And that was all done with bear actors. Okay, so we have two quarter wave vertical antennas. And if we space them a half wavelength apart and we feed them 180 degrees out of phase, we're going to get a figure 8 pattern that is oriented along the path between the line between the two antennas. So you've got an antenna here, so you got a figure 8 pattern between the two. If I space them a quarter wavelength apart and I feed them 90 degrees out of phase, I'm going to get what's called a cardioid pattern, which means it looks like a heart. So it'll have a rounded beam and a null point. And it's actually one of the patterns that's used for direction finding or fox hunting, where you don't look for the maximum signal, you look for the null. So you can detect the signal all around on the cardioid, but when you've got the null pointed out at the source and you're no longer picking up the signal, that's where it is. So it's a lot easier to do it with the null than it is trying to do it with the peak. And then if
you need for that?
Huh?
How many antennas do you need for that?
For the cardioid,
to find the null?
well, each two antennas quarter wave will give you a cardioid pattern.
Okay.
You can do it with a 3-element Yagi if you do the right spacing, where you don't set it up for maximum gain. You can actually change it where you get a 50 dB null in the backside.
So we used to use the direction finder in the civil air patrol from ELTs, emergency beacons. And it was just two dipole antennas with a phase detection unit in between to tell which one was closer to zero.
Yeah.
So and it was using signal strength and or which one was
Yeah.
closer. So
You always used to see them use loop antennas,
yeah,
but the problem with the loop antenna is it's both ways.
right.
And you have,
That's the thing we had to deal with the two dipoles, because they
Yeah.
couldn't go ways.
yeah.
Yeah.
And then you can have the antennas half a wavelength apart again and feed them in phase. And now you get a figure 8 broadside to the axis. So essentially you're creating a half wave dipole effect without the wire in between, with just two vertical quarter wave antennas. You get the same kind of pattern where it's perpendicular to the line between them. So if you remember those three, which I always had trouble, let's see how you do. This is what the figure 8 pattern along the axis looks like. This is a cardioid where we're quarter wave apart and 90 degrees out of phase. And this is half wave apart, 180 out of phase. So you get this almost identical pattern you would see if it was a half wave dipole. Any questions on those? Okay. What type of radiation pattern is created by two quarter wavelength vertical antennas, half wavelength apart, 180 degrees out of phase? Delta. Everybody get that?
We did the hyperlink button.
Well, I knew it was C and D, and I was wishing I'd given attention to the finer pieces part of it. I had better.
That's one you just have to remember.
Okay.
What type of radiation pattern is created by two quarter wave antennas, quarter wave apart, 90 degrees out of phase?
That's how fun, yeah.
Okay. Because that was different, we're quarter wave apart. That was easier to remember. What type of radiation pattern is created by two quarter wave antennas, half wavelength apart, fed in phase? Now, we've already done the other two. So. Anybody got Charlie? Okay. Like I mentioned before, things affect the antenna, especially ground. So depending what is underneath your antenna is going to affect the pattern. And the little chart over there is showing, if you can detect the colors, that outer loop, the green one, is the radiation pattern where the antenna is over salt water. You can see how much better it is. And then they go down to these ones in the middle. That red one, I guess, is poor. I'm not sure what. I guess that's blue. That's moderate. For some reason, poor does better than moderate. I don't know why. But you can also see that the takeoff angle gets lower the better it is. So you'd say the takeoff angle for this one over saltwater is probably down here somewhere. Where you're gonna be up here and on up. Because you find the maximum point on the load. So it increases or it decreases the takeoff angle also. And this is done for a vertical antenna, which has the toroid pattern around the vertical. So that's an elevation plot. Oops. So how is the far field elevation pattern of a vertically polarized antenna affected by being mounted over seawater versus soil? Delta increases or it decreases the takeoff angle. If you're on the side of a hill, it has an effect where the takeoff angle on the downside of the hill will be lower. It sort of follows the slope of the land a little bit. So if you're on one of these islands down there doing islands on the air and you're on the side of their little mountain, then you get a very good low takeoff angle in that particular direction. If you've got a beam antenna like a Yagi, the pattern changes, and it actually on most antennas, the pattern changes depending on its height above the ground. So in the case of most of those, the takeoff angle keeps getting lower, like I said before, the higher it is, but also the higher you go, the more extra lobes you start getting. So you wind up having less power, even though you got a lower takeoff angle. So it's like most things, there's a compromise. How does the radiation pattern of a horizontally polarized antenna mounted above a long slope compare with the same antenna mounted above flat ground? And remember the difference between increase and decrease. Amy says B. How does the radiation pattern of a horizontally polarized antenna vary with increasing height above ground? Is it?
I think.
It's so. Right. Yeah, some of these you have to read carefully. When you do the exam, read the question, read all the answers before you answer. Because sometimes you'll see, well, oh, that's right. But there's one word in there that made it wrong. There are many different kinds of wire antennas, so we're going to talk about some of those. Long wires, folded dipoles, off-center fed dipoles, ZEPs, which is a type of end-fed And the G5 RV, which I brought one, just if you want to see one. I've yet to string it up. Only had it for a year. Because I need 102 feet. So a long wire antenna is basically an antenna that's, they usually say more than a wavelength long. Over here on the right-hand side, we're showing one that's 1.25 wavelength. And you can see what the pattern is. It's along the axis of the wire. And the longer it is, the more lobes you get, and they stretch out along the wire. So it becomes more and more directional. For it to be resonant, excuse me, different frequencies, it needs to be in multiples of half wavelengths. So you can have it a half wavelength, a full wavelength, 1.5 to 2.5. They won't have or they will have a very high impedance that you feed it with. So you'll need a matching network. This is somewhat like an end-fed. They don't call it that, just a long wire. What happens to the radiation pattern of an unterminated long wire antenna as the wire length is increased?
That's it.
Get additional lobes, but they're all aligned along the axis. Okay. I don't know if anybody here remembers making TV half-wave dipoles out of 300 ohm feed line. Was a common thing to do. They still work. It turns out that just by nature, they have approximately 300 ohm impedance. So it works perfect using 300 ohm TV line. Always used to make one of those real quick and tack it up on the wall, and you could get TV reception. And if you made it the right length, you could get FM very well on your radio. Basically, it's a half-wave dipole with a parallel element that's a half wavelength long. So you're making it a full wavelength loop. It's just they're very close together. So it acts a little bit different than like a quad, which is still be one wavelength all the way around. But normally they're it's either circle or a diamond or a square, so the sides are essentially equal. This is a plot in EasyNet I did for that, and you can see with it being fed at 300 ohms, you get a little bit better than 1-to-1 SWR at whatever frequency that is. And I can't read it off here. Well, actually, I can. It's 7 megahertz. So you could use that on the 40 meter band. What is a folded dipole antenna?
See.
Charlie, half-wave dipole with a parallel, basically a parallel wire. What is the approximate feed point impedance at the center of a 2-wire half-wave folded dipole?
300.
300. If it was just the dipole, it would be 72. When you add the extra wire, it changes the impedance a lot. We have what's called a Wyndham. Most people just call it now, you see them as off-center fed dipoles or OCFDs. I guess when it was originally invented, it was called a Wyndham, probably the guy that invented it. So you feed it instead of the center about a third of the way from one end. And it gives you multi-band operation because you get trying to think which harmonics you get. Probably on the next chart. You get some of the harmonics on it. Maybe it's even. Because on an end fed, you get most of the harmonics. So they're saying in this case, if you do it for 80 meters, you're going to get a pretty good SWR on 40, 15, and 10. This is kind of a diagram where it's at around a third of the way, fed with a balun and 50 ohms. And these are the different patterns that you see on the different bands. So since it's half wavelength for 80 meters, you get the standard figure 8 broadside of the wire. As you go higher in frequency, then you get more lobes. So you get these cloverleaf patterns and you keep getting more and more lobes out there. And this is horizontal. If you looked at it vertically, you'd be seeing the same kind of vertical lobes also. This is another easy neck plot. If you fed it at 25% versus 33.33%. So it changes the pattern a bit. So in some cases, you get some better SWRs, but not necessarily at amateur radio frequencies. What is the purpose of feeding an off-center fed dipole between the center and one end instead of the midpoint? Alpha. You get a similar impedance on all the bands. Well, multiple bands, I should say. Okay. The ZEP, I believe the story goes that that's what was used on the Graf Zeppelins by the Germans. And it was an end-fed half-wave dipole that was strung under the balloon. It has a very high impedance because you're feeding it on the end. So you have no current and maximum voltage. So the impedance is in the thousands of ohms. In this case, it's slightly different in that they're using a quarter wavelength piece of transmission line as a impedance transformer to feed it as instead of using a balun, which we normally use on an end fed today. And then there's the extended double ZEP, which I'm not sure how it relates, but maybe it's because the same people use it. It's a center fed antenna where each element is 1 1/4 wavelength long. Or excuse me, the whole antenna is 1 1/4 and the elements are 5/8. So it's totally different than the regular ZEP. This is what the classic ZEP looks like, where they're using some ladder line. They're picking a point, it's shorted on this end, it's quarter wave long. So they're picking a feed point where it looks like 50 ohms. If you remember, if you take a quarter wave piece of wire or transmission line and you short one end, it looks like an open circuit at the opposite end, and vice versa. If you leave it open, it looks like a short at the opposite end. So anywhere along that quarter wave line, it has a different impedance. And that's how we do a lot of matching networks, by using that effect and picking a point where it's the impedance we want. In this case, it's 0 down here where it's shorted, so a few inches up, it's going to be 50 ohms. Up at the top, it's going to look like an infinite. Actually, I think it'd probably even be a better match if you moved it down a little bit to get the right impedance match at that end. But it seemed to work this way. In the case of the double ZEP, they feed it the same way, except they're doing a balun to match between the 50 ohm line and this 450. I'm not sure, but the center impedance may be close to 450 in this case, which is why they're doing it that way. This is what a plot looked like for the ZEP. And you see it's got harmonics all over the place. And everything on there is below 2-to-1 SWR. So you could probably pick up every band that there is, not just US amateur. Which of the following describes a ZEP antenna? I think it's the original in-fed half-wave. Which of the following describes an extended double ZEP? Charlie. Okay, the G5RV is a multi-band, also dipole, fed in the center through ladder line and a balun. It's different in that it's not a half wavelength. I guess the guy that originally came up with it was doing it as trying to optimize a 20-meter antenna. They claim you can tune it to other frequencies. I don't know. I haven't tried mine.
That's why I run this G5RV.
Okay.
Yeah, I can.
So you have enough room.
Yes, I can get out. And mine's actually an inverted V
Okay. That's what I'm going to try.
configuration. But yeah, I can tune 80 to 10. I can get out of the warp phase too on it. So I don't think it was made to do that, but 20 is definitely 20 meter. Favors 20 meter.
What kind of SWR you get without tuning it?
I haven't checked without tuning it. So I've got an auto tuner built in that I actually shut off because I like to actually MFJ actual manual
Right.
tuner. So I
Play with the knobs.
well, yeah, I get it tweaked in and dialed in. So I want to make sure that everything's in. I don't trust the auto tune.
Yeah. Okay. Well, that's what it's supposed to look like, where it's 51 feet on each element with the 450. If you're not familiar with window or ladder line, you can kind of see some there. It's a bigger version of 300 ohm with holes cut in it just to improve the dielectric. And it's about an inch wide as opposed to the 300 ohm is probably a half inch wide. They also make a wider one that's 600. It's a couple inches. I'll usually call that ladder line. These are the patterns that you supposedly get for the different bands. So we got 80, 40, and 50, 30, 20. So you're getting patterns out on all of these, but like the others, you start getting these cloverleaf kind of patterns. Where at 80 meters, it's basically omnidirectional. So it's sort of like having a vertical. And then at 40, it's going to look more like a regular dipole. Oops.
Hey.
I'm supposed to shut your eyes. Center fed, specific length of open wire connected to a balun and a coaxial feed line. Rhombic antenna, I've never seen one. These take up, especially for the lower bands, a lot of room. I've seen pictures of like antenna farms where they have a bunch of these down in the very low frequency ranges where it's set up to make a connection at a specific direction. The one downside is that it requires, to make it unidirectional requires a terminating resistor where it's a bidirectional pattern if you leave it open. If you wanted to have a unidirectional pattern, then you have to put a termination resistor on there. So that kind of limits using it as a transmitting antenna. And this shows the difference in pattern. If it's terminated, it's very much like a Yagi, except it's got a lot more side lobes on it. Where when you have it unterminated, you sort of have that duplicate pattern, but it's mirrored. What is the effect of adding a terminating resistor to a rhombic antenna? Changes the pattern. We have a couple more coming up where you're going to have that same effect. Oh, they're here.